Good morning. We were looking at the property of a ferromagnetic material when it is subjected to an MMF in the last class, and I was drawing the characteristics which is known as the magnetization characteristic of a ferromagnetic material, which is drawn between, you can say, either MMF and flux. This is one way of saying it, where MMF is the root cause and flux is the effect. This is one way of saying it. Rather than that, if I just say MMF per unit length of the magnetic circuit, I can say this is directly between H, which is the magnetic field intensity, and the flux density, which is again flux per unit area. Okay, so I can draw between these two. When I draw the characteristic, generally as I increase, let us say I'm going to have a ferromagnetic material somewhat like this. This is what I'm showing as the ferromagnetic material, maybe a three-dimensional one. And I'm going to have the wire which is going around somewhat like this. So I'm going to have something like this coming up, and I'm going to have the current flowing through this wire, and N is the number of turns. So I am essentially looking at current which is coming out here and going in here. So this is going to be dot and this is going to be cross. So because of which I'm going to have a magnetic field which is produced in this direction. So it is going to be in this direction. Okay. Now, when I am taking a new sample of iron and subjecting it to a magnetic field intensity H or an MMF, I'm going to see that initially the flux increases and then at some point it is going to reach saturation. It's not going to increase any further. Okay, so this is going to be the way how a new sample of iron behaves. But in this particular sample, if I try to reduce the current or MMF, it is actually going to be pretty obstinate. It is not going to come down in terms of its magnetic flux density, but after a lot of reduction in the value of magnetic field intensity, I'm going to have this particular flux retracing the path somewhat like this. So this is going to be the path in which it is going to come down. But when the current becomes zero or the magnetic field intensity becomes zero, even at that point there is some finite amount of flux or flux density that is left over. So this, if I may call as O, and let me probably call this as A, and let me call this as C. So I'm going to have OC as the flux density left over even when the current is zero or when MMF is zero. I'm not going to have any MMF, but still there will be some flux left over. So this OC is generally known as the remnant or remaining flux density. Even at zero current, this is going to remain. Now, after this, if I try to increase the current in the opposite direction, okay? So in that case, I'm going to see that this is going to increase from here. Maybe it is going to again reach saturation somewhat like this. And from here, if I try to again decrease the current, it will actually go through the same kind of cycle and it would just go through the opposite way. This is the kind of loop it is going to have for the variation of B with respect to H. So we call this as BH loop. BH loop essentially indicates the variation of flux density with respect to the magnetic field intensity. So this is BH loop. So in BH loop, if I try to look at it, if this is O, I am going to have O to A initially as the variation when I am taking a new sample of iron. And when I am trying to reduce the current through the coil which is wound around this ferromagnetic material, it is going to come down, but it is going to come down very reluctantly. It is not going to come down very easily. So I'm going to see that at a point where I'm going to make the current zero, still there is some flux density remaining, which is known as OC, which is known as remnant flux density, which is given by this ordinate OC here. Now, after I increase the current in the opposite sense, it is going to actually reach zero flux density only after I increase the current to a negative value by certain amount. So if I call that as OD, so OD is the coordinate, x side coordinate, which is actually corresponding to a negative current. That is going to make sure that the flux density is brought to zero. So that actually coerces the flux density. It forces the flux density to come to zero. So this is generally known as coercive force. This is going to be called as coercive force. This is called coercive force. Okay, so this is coercive force. Now when I increase the current further in the negative direction, I'm going to call this point as E. So I see that it has reached again a saturation as far as the flux density is concerned in the negative direction. So that is point E. Now from here, if I try to decrease the current further, or it has to come towards zero, then at zero current, it is still going to maintain certain negative value of flux density. And let me call this as F. So OF is going to be again remnant flux density, but in the reverse direction. Now here, if I call this as G, this G is going to be the coercive force on the positive direction, which will bring down the flux density from a negative value to zero. So this is the way a piece of iron or a ferromagnetic material will behave whenever you subject it to the positive current and negative current. So whenever you are going to subject it to an alternating current excitation, then it is going to go from G, it will go towards A, and from A it will come towards C and D and so on, and then it will come to E, and then this will just repeatedly happen. So I can say A, C, D, E, F, G back to A. This is actually my hysteresis loop, or the ferromagnetic materials hysteresis loop. So why does the behavior of a ferromagnetic material different from that of a non-ferromagnetic material like air or vacuum or wood or something like that? So let us try to look at behavior of ferromagnetic material, why it is different from that of rest of the kinds of material. If you look at iron, iron generally has 4 electrons in its outermost orbit. Okay, and if you look at normally the electrons, apart from they go around the nucleus, they also have a spin around themselves, around their own axis. So all the electrons spin as well. But in other elements, if I have 4 electrons, all of them will spin in all sorts of different direction. Whereas in iron, it so happens that if this electron is spinning around this axis like this, This is also going to spin in a very parallel, in another same kind of direction with a parallel axis, and this one also will spin in the same kind of parallel axis. So all of them are going to spin, all four of them are going to spin in a direction such that their axes are parallel to each other. And when a charged particle is spinning, it is as good as a current ring is created, because flow of electron is current. Here electron is basically spinning, because of which you are going to see that it is creating a current ring. So you are going to see a current ring created whose axes are parallel to each other. So they are going to create magnetism, because whenever you have a current ring, you are going to have a magnetism which is actually perpendicular to that particular spinning direction. So you are going to have magnetism created by all these four electrons in a particular direction. So if you look at any iron atom, it is going to inherently have a magnetic domain or magnetic moment created in a particular direction. So if they are creating a particular direction based magnetic moment, and generally what happens is, if this is the complete piece of iron, it is generally divided into domains, and each domain is going to have about a width of 10 power minus 4 meter. That is 0.1 millimeter. So that is the kind of width each domain is going to have. And within this domain, we have several atoms, and all the atoms are going to have their outermost orbit electrons spinning along the same direction, because of which every domain is going to have a magnetic moment. Probably this is going to have a magnetic moment in this direction, whereas this may have a magnetic moment in this direction. This may have a magnetic moment in this particular direction, whereas I may have one more domain having a magnetic moment in this direction, and so on. So I'm going to have many of them having magnetic moments in all sorts of different directions. So when you take a new sample of iron, although each domain has a finite magnetic moment, when you look at the entire piece in totality, all these magnetic moments cancel with each other. So you are going to see that the net magnetic moment that is available from a new piece of iron, when I look at the net magnetic moment available, that is going to be 0, because they are all arbitrarily, randomly, going in all different directions. Okay, so that is the reason why net magnetic moment will be 0 for a piece of iron. New piece of iron. Now, between one domain to another, there is something like a dividing wall, and this dividing wall will be of the length of about 10 power minus 4 millimeter. So compared to this 10 power minus 4 meter, which is the width of this, 1,000th of that is going to be the dividing wall's thickness. So slowly it is going to change its magnetic moment direction from here to probably here. And similarly from here to this kind of a direction. So it is going to change the magnetic moment direction from one particular direction to another through the wall, which is of 10 power minus 4 mm thickness. So what happens is, when you subject this piece of iron, let us say I wind a coil around this. I'm going to wind a coil around this, and then I'm going to pass a current through this. So let us say I pass a current through this. So what is going to happen is, this is going to create probably a magnetism in a particular direction. So this is going to be the flux density's direction. If this is the way it is, all these magnetic moments which are inherently available within the domains of the iron, all of them are going to slowly align themselves because of the current that is being passed through this coil which is wound around. So, whenever you have air surrounding it, the air is not going to have these inherent magnetic moments available. So, what you create as the flux is because of the current that is flowing and the magnetism that is created extrinsically. So, we call this as extrinsic flux. What is created in air or any other non-magnetic material. There is nothing inherently available within that material. Okay. So, in non-magnetic material, whatever is created, that is called extrinsic flux. But in iron, these intrinsically available magnetic moments are going to be aligned. So automatically you will see a very, very large increase in the flux as well as flux density in the case of iron, because intrinsically there are magnetic moments that are available. They are going to be slowly aligned. As the strength of the current increases further and further, more and more of these magnetic moments are going to get aligned. It is like you are doing physically a work on these magnetic moments and you are trying to move them in alignment with the extrinsic flux. So what will happen is, when the current increases, initially you see that more and more number of magnetic moments are being worked at, and you are doing work on it, or the external current is trying to work on these magnetic moments to align them along with the extrinsic flux, because of which the flux is going to increase quite a bit. But beyond a particular point, all these magnetic moments have been aligned. So hardly there will be any more increase in the flux. So that is why once all these magnetic moments are aligned along with the extrinsic flux, you hardly see any increase in this flux density anymore. It reaches the maximum value and that's it. There cannot be any more increase. So this happens once all the magnetic moments are aligned. If you look at this, this is the intrinsic flux. Whereas if you look at the extrinsic flux, what is available because of the air molecules or whatever that is available, so that is essentially going to increase at a very, very small rate. It will hardly increase much. So this is going to be extrinsic flux. In fact, the ratio I have shown is not correct. Like what I told you, in many of the ferromagnetic materials, we are going to have the relative permeability to be anywhere between 300 to about 4,000 or even 15,000 in some cases. So the extrinsic flux will be 1 by mu r times whatever is the intrinsic fluxes. So we are going to have very, very small amount of extrinsic flux, although that will increase with the current. That increase is very, very meager. That is the reason why you see hardly any increase. So this is going to be a constant value beyond saturation. After saturation, you are going to see that this is going to be a constant value. Okay. So once they are all aligned, they are kind of, they don't want to be disturbed from that position because already work has been done on them. And if you try to now reduce the current, so you are trying to reduce the current. So when you reduce the current, it's not going to be easy for those domains to be disturbed from the existing position, because still there is the extrinsic flux which is along a particular direction that is not going to really allow these domains to be moved or disturbed from their original position. But once the current becomes zero, still many of the moments are obstinate. The magnetic domains are obstinate. They are not going to change their position, or they are not going to budge from their position. But only after you apply a current which is actually in the opposite sense, and the current strength increases to certain extent to coerce the other magnetic moments which have been obstinate to change their direction as well. Only after that the flux density is going to become zero. And beyond that, again, these moments will start aligning along the extrinsic flux, but in the opposite sense, because the current is in the opposite sense and it is going to become saturated in this particular direction. And the same thing repeats itself when you are trying to increase the current in the positive direction. So this is the way you are going to see the BH loop, because of the magnetic domains that are inherently available in a piece of iron, which is because of all the four outermost electrons rotating in a particular direction along their axis being parallel to each other. That is the reason why you are going to get this kind of intrinsic flux, and that is one reason why when you put a ferromagnetic material, the amount of flux density you see will be much higher than what you see in air, which is due to extrinsic flux alone. Okay. Now, when you are subjecting a ferromagnetic material to this kind of a current, that to alternating current, let us say I am talking about a small value of H. Maybe I am talking about a finite value of H. So let me call this as O and let me call this as some P. So OP is a finite value of H. At this point, I'm going to have a flux density which is corresponding to this particular value. Okay. So I'm going to have this particular value. Let me probably just redraw this once again. So let me say that this is my B axis and this is going to be H axis, and I'm going to have something like this. So from here it is coming down and from here it is going up like this. So this is the BH loop that I am looking at. So let us say I am looking at a point where this H value is OP. So this is the H value. OP is the H value at this particular point. So if I try to look at, if I disturb it slightly from OP, I try to make it as OQ, then I'm going to have a very small increase in the flux density, which I may call as dB. So dB is the incremental increase in flux density when H is slightly increased, which is from OP to OQ. So I can say dB divided by dt multiplied by the area of the core multiplied by number of turns that are actually wound in the coil, which is creating this magnetic field intensity. This I can write as N d phi by dt, because B multiplied by A is the area. So I can write like this. This will be the induced EMF. Right? Because N d phi by dt will be the induced EMF. Now, this induced EMF is actually going to kind of resist the change of the magnetic domain's direction. So to make them change their direction, you have to necessarily apply a voltage such that it is going to push these magnetic domains to do the work of turning around completely. So this induced EMF, if I may call as some E, I have to apply a voltage to neutralize this induced EMF's effect, which is actually preventing the domains from shifting their position, because they are not going to give up their position so easily. Now, this is the voltage that you have applied, but simultaneously a current I is definitely flowing through this coil, which is creating the extrinsic flux, which is actually the root cause for all these magnetic domains to align themselves along the extrinsic flux itself. So, if I say power that is being supplied to this magnetic material to align the domains along the extrinsic flux, along the direction of the extrinsic flux. So this is actually whatever is the EMF multiplied by the current. So I should be able to write this as NA dB divided by dt multiplied by I. So I should be able to write it like this. Okay. So NIA dB by dt is the power that is being supplied to align the domains along the extrinsic flux. Now, if I supply this power for a duration of dt, so energy given to the magnetic material for a duration of dt, that will be I N A dB multiplied by dt. So this is going to be the total amount of energy that is given to the magnetic material when we are trying to align the domains along the extrinsic flux. Now, after all, if I'm going to say that this magnetic material is this, and I am winding a coil around this like this. So I can say the length of the magnetic material, if it is L, I'm going to say Ni divided by L is H. Or I can say Ni equal to H times L. So if you look at this particular expression, I can replace this Ni by H times L times A multiplied by dB. So this is essentially the amount of energy supplied for an increase in the flux density by an amount of dB. So which is given by this small strip. So I can actually do the complete integration. So if I try to do the complete integration right from, it is starting from zero flux density until maximum flux density here. If I may call this as Bmax. And similarly, this is minus Bmax because it will be symmetrical. So if I'm going to have Bmax and minus Bmax, and if I try to do that entire amount of energy that is supplied for the domains to align in the positive direction and again realign in the negative direction. If I try to do that, I will get the complete area under this BH loop as what is the energy spent over one cycle. So I should be able to write this as integral of H dB will be equal to the area under BH loop when the flux is continuously changing from plus B max to minus B max and back to plus B max. This is one cycle, complete one cycle. So this is going to be the energy that is given to the magnetic material per unit volume. Please understand this L times A is actually the volume of the magnetic material itself. So this is going to be the energy lost when aligning and realigning the magnetic domains. But this energy lost will be joules per meter cube. And please understand this will be per cycle. If I'm going to subject this material to an alternating current, if I am passing alternating current through this, okay, so this will happen 50 times in one cycle, in 1 second, if I am using a 50 hertz supply. So this is going to align and realign repeatedly when I am actually applying an alternating current for this particular excitation, and this magnetic material is continuously going to have its moments aligned and realigned, which means it is an unnecessary job done, can't help it, but that is going to result in physically aligning and realigning these magnetic moments, because of which there will be a loss. So whenever we talk about hysteresis loss, this is what we mean by hysteresis loss. So hysteresis loss is the power loss that is incurred by the magnetic material, by the core material. Invariably in an electrical machine, the magnetic ferromagnetic material will be used as the core. So power loss incurred by the core material when aligning and realigning its magnetic moments when, because of being subjected to AC excitation, alternating current excitation. So if I had given only direct current excitation, this is not going to happen, because once it has aligned all the magnetic moments in a particular direction, you don't have to realign them. Whereas in AC, repeatedly you have to align and realign. So the hysteresis loss, what you see again, hysteresis loss, what we see in a magnetic material is because of the property of the flux to lag behind. So flux lags behind the current, and the magnetic moments are aligned and realigned. And that is the reason why the higher the frequency, you are going to see, because hysteresis loss we said is area under BH loop. This is hysteresis loss in terms of joules per meter cube per cycle. So if I want, if I just multiply this by cycles per second, which is actually hertz, I'm going to get joules per meter cube per second, which is actually watts per meter cube. Joules per second is watts, so watts per meter cube. So I'll get hysteresis laws in terms of watts if I am actually looking at the area under the BH loop and multiply that by the frequency of the excitation current. That will give me watts per meter cube. So if I multiply that by the length of the magnetic circuit and the area of cross section of the core, I'll get completely whatever is my hysteresis loss for the magnetic core that I am talking about. Okay. So hysteresis loss plays a very vital role when we are calculating the overall efficiency of an electrical machine, because this is going to be proportional to the frequency of the supply, and it is also going to be somewhat dependent upon what is the B max value at which I am making my machine work. If my machine works at a larger value of B max, I'm going to have definitely the ordinate what I get in terms of B. This is B max and this is going to be minus B max. So I'm going to have a larger area under the hysteresis loop. So if I'm going to work at a higher and higher flux density, in all probability, I will have a higher value of hysteresis loss as well. So the hysteresis loss mainly depends upon two things. One is what is the frequency of the supply. That is one thing. And the second thing is what is the value of B max at which I am making my machine work. So these two are going to decide what is the hysteresis loss. That is one reason why whenever we use a very high frequency apparatus, there are transformers which work on hundreds of kilohertz. So whenever we are going to talk about high frequency apparatus in general, maybe it can be a transformer, maybe it can be an electrical machine. Whenever we talk about a high frequency apparatus, we should use the core material having very narrow BH loop. If it has a narrow BH loop, then the area under the curve will be small, which means I'm going to definitely get less amount of hysteresis loss from this kind of a core material. So that is one reason why in many of the high frequency transformers, we generally use either something called ferrite core, where you are going to have very, very narrow BH loop, or we will use iron filings. That is, it is like grating. When you have some kind of, filing and other things done for your smithy and foundry, whatever you do, generally you must have done in the workshop, or you must have seen those things where you try to take out some portions of iron and you want to shape it to a particular shape. So in that case, you will have small pieces of iron, filings of iron. It is like carrots that are being grated. You see small pieces of carrot coming out of the grating apparatus. The same way, these iron filings are basically small little pieces of iron, because of which they must have already lost some of their domain orientation. So if they have lost their domain orientation, they will not be in a position to really, be obstinate, or they will not be able to really maintain their magnetic orientation very strongly. So generally, what is done for high frequency apparatus is either you use a ferrite core or you fill these iron filings into some kind of non-magnetic material. So you can have a fiberglass tube or something like that, and you just put it into some non-magnetic tubes and then use them as your core material around which you will try to wind the windings of the transformer or the electrical machine. So this is what is done generally whenever we want to reduce the hysteresis loss in an electrical machine. Otherwise, if you want to completely avoid hysteresis loss, only way is to use DC, not AC at all. Okay, but AC is of course very useful because of various other reasons which we talked about in the initial classes. You can step up and step down AC, which you cannot do so easily with DC. That is one reason why you generally we have resorted to AC transmission, AC power usage rather than DC, because you are able to step up and step down, and you are able to transmit it at extremely large voltages. So if I try to look at what is power, power is going to be V multiplied by I. So if I increase, if V is increased with the help of a transformer, that is stepped up with the help of a transformer, then you are going to reduce I. So at lower value of I, you would be able to get the same power. So lower the value of I square R losses in the transmission line can be decreased. So that is the reason why you are going to see that normally, high voltage transmission is the one which is very commonly used. We never transmit the power at very low voltages, not at 400 volts, not at 230 volts. It is always transmitted at 465 kV, maybe 700 kV, maybe 800 kV. So we always try to transmit, these are the transmission level voltages. Okay, but because we do this stepping up action with the help of a transformer, it always has to be AC, not DC. That is the reason why we always use AC transmission and not DC transmission. Okay. Now that you have at least some idea about magnetic circuits, you have some idea about the behavior of ferromagnetic material, we are going to start now on electrical machines. We will only see the fundamentals of some of the electrical machines. So in electrical machines, specifically, we have a static machine, which is actually the transformer. It doesn't have any rotating parts. So this is not going to have any moving part. No moving part in this particular machine. Okay. So we will start with this, which is actually one of the simplest electrical machines. And we will go towards rotating electrical machines. And I would only give an introduction to some of the rotating electrical machines, nothing more than that. So if you look at rotating electrical machines, there are DC machines. And the second one is AC machine. So in AC machines, there are two types of AC machines. One is going to be induction motor or induction machine, and the other one is synchronous machine. And again, these AC machines can be from single phase or they can be working from three-phase supply. So if I am looking at it as a generator, it can generate single phase supply or three-phase AC. If I'm looking at it as a motor, it can be running from single phase AC supply or three phase AC supply. So we will be looking at all these things superficially with respect to the AC machines as well as DC machines. But first thing that we are going to start is the transformers. We are going to look at transformers first. Okay. So the transformers, if you look at it, as I told you, it can be used for either stepping up AC voltages or stepping down AC voltages. So it cannot really work with DC at all. This will not work with DC. So basically what we actually see in a transformer is there are mainly two portions. When I try to look at the construction of a transformer, it is going to have two main portions. One is the core, second is the winding. These are the major two portions of a transformer. So we are going to have the core somewhat like this. I'm going to just show the core as though it is like this. Okay. So a primary winding may be wound on one side. I'm showing this notionally, basically how the transformer really functions initially. We'll talk about the construction little in greater detail a little later, but this is going to be my primary winding, to which I'm going to apply the AC voltage that I want to step up or step down. So I'm going to show an AC voltage here. So this is the AC voltage that is being applied here. And on the secondary side, I'm going to have again certain number of turns. Okay. So what is going to happen is that I am actually trying to extract the output from this side. So this is going to be the primary current that is flowing. And this primary current is actually going to create a flux somewhat like this. So this is going to be the flux that is created. I'm showing one flux line basically. So this is the flux line that I'm showing. So magnetic flux lines are going to be created along the core. The core is essentially there to make sure that all the flux lines, as much as possible, they are all channelized through this. They are all channelized through the core itself. Because they are all channelized through the core, you would hardly see any flux lines going like this. As much as possible, you are trying to avoid the leakages. So, by using a ferromagnetic core, you are trying to maximize the flux that is linking with both primary and secondary. So, the primary coil is getting a current because of the voltage that you have applied. So, let me call this as V1 or Vp. Okay. Now, this is creating actually a flux. So, let me call that flux as phi. So if I say V1 equal to some Vm sine omega t, I am going to have the flux also almost having a similar kind of variation. Okay. So I'm going to have again the flux that is created in the core is going to have this kind of a variation. Now, as per Faraday's law of induction, I'm going to have N d phi by dt as the induced EMF. And this induced EMF definitely will happen in both primary as well as secondary. I want you to understand this clearly. If a flux is created through the core, please understand the primary coil is also subjected to that flux. The secondary coil is also facing that flux. So if I am going to have N2 turns here and N1 turns here, I am going to have actually the primary induced EMF, if I may call that as E1, which is the induced EMF in the primary coil. That is going to be equal to, if I assume that all the flux that is linking the primary is also linking with the secondary, both of them are equal. In that case, I'm going to have this as N1 multiplied by d phi by dt. The same way, I'm going to have E2, which is equal to induced EMF in the secondary coil. And that is going to be N2 multiplied by d phi by dt. That is going to be N2 multiplied by d phi by dt. So I can say E1 divided by E2 is equal to N1 divided by N2. So if I say that the induced EMF here is E1 and the induced EMF here is E2, and if I put a voltmeter here and measure what is the voltage, that will be same as E2, isn't it? So I'm going to have the terminal voltage that is seen on the secondary coil and the terminal voltage or the induced EMF that is seen on the primary coil. If I take the ratio, it will be essentially N1 by N2. So this is the way the transformer action works. So the transformer action is because of the flux originally created in your core of the transformer. The core of the transformer gets a flux because of the primary carrying a current. The primary coil carries a current because I have applied a voltage to the primary. So this V1 is an alternating voltage I have applied to the primary. The primary has a current flowing through it. Because of the current that is flowing, you are going to have a large amount of flux established. Why do I say large amount of flux? Because this is MMF divided by reluctance. That is going to be the flux that is established. And the reluctance is generally very small for a ferromagnetic material. So even for a very small MMF or a very small current, so even for a small current carried by the primary coil, I am going to have a large flux established. We are going to have a large flux. So this flux is going to confine itself as much as possible to the core because surrounding air and everything is going to have a much larger reluctance. So whatever flux is created in the core because of the primary coil current is going to definitely link with the secondary coil as well, and the secondary coil is going to get an induced EMF as well. The secondary coil induced EMF, if I call it as E2, that will be N2 multiplied by d phi by dt. That's what it is going to be. So N2 multiplied by d phi by dt, and the induced EMF in the primary will be N1 multiplied by d phi by dt. So these two are going to be in the ratios of their respective number of turns. So if I put larger number of turns in the secondary as compared to the primary coil, I'll get a step up action as far as the secondary is concerned. If I put smaller number of turns in the secondary coil, I'll get basically step down action as far as the voltage is concerned. Okay. So We will continue with transformers further in the next class as well. So I have only given a basic introduction to the transformer.